Now in this lecture we see the inverting and non-inverting amplifier and we derive the expression for the inverting non-inverting gains. Now here the inverting amplifier. So before deriving the gain, now let me explain how to draw the diagram for the inverting amplifier. So now here I am taking the operational amplifier. For that, so now this is the symbol. Already symbol I have explained in the first lecture. So inverting terminal I am taking, non-inverting terminal I am taking, and here I am using two resistors. Now, here heading is inverting. So negative terminal is called the inverting terminal and positive terminal is called the non-inverting terminal. So we need to apply, in inverting amplifier we need to apply the signal to the inverting terminal. Now here I am applying this signal. So this I will take it as a VI or Vs. So and this is the output voltage, and here I am applying the plus VCC and minus VEE. So supply is we have given, and this is the inverting amplifier. That's why non-inverting terminal directly I am connecting to the ground. And here we need to apply the feedback. In the unit 3 we have studied the two different types of feedbacks. First one is a positive feedback, negative feedback. Now this is the amplifier. In an amplifier we use the negative feedback. What is feedback? Taking part of output and again fed back to the input is called the feedback. Now here I have to take the output and I need to apply that signal at the input. Now which input I need to connect? Here two inputs are there, but I have to apply that output value to the negative terminal, then only it is called the negative feedback. If I apply the output to the positive terminal, then that is called the positive feedback. In an amplifier we use the negative feedback. That's why now here from this point to this point I have to connect one resistor. Okay, now this name I am giving it as a R1 and this name I am giving it as a R2 or RF. Because it is a feedback resistor, we can denote it as a RF, or if you wanted to denote like R2, then that is also fine. Now here we need to calculate the gain. This is an inverting amplifier. When we apply the signal over here, it will amplify the signal with the gain. Now what is V out? V out is equal to gain into AV or A into V in. Now what is A or AV? Voltage gain or A. Now here I can write it as a AV or A. So what is voltage gain? That we need to derive the expression. Now here, because we are applying the signal to the negative terminal, so at the output we are going to get the 180 degrees phase shift. Means now here if this is my input signal, then at the output I will get the amplified signal with 180 degrees phase shift. So this is my output. So I will get 180 degrees phase shift because we are applying signal to the negative terminal. So now here what is gain? How much it will amplify means we need to know about the gain. So how to derive the expression for gain? For that you should have a knowledge of, now here I am applying for all the applications I am applying the nodal analysis. So what is nodal analysis? It is nothing but applying KCL only, Kirchhoff's current law, but assuming one thing that all the currents are leaving from that node. Now where I need to apply, now if I am taking this as a VA and this is a VB, and here, so how many number of branches are connected total? So this is one branch, this is second branch and this is third branch. So total 3 branches are there. Now for this I have to apply the KCL. Now before that let me explain. Here I have taken the current into the amplifier, but now in the input impedance, now in ideal case what is the operational amplifier input impedance? It is infinite. So inside the amplifier there is infinite resistance, or you can say practically very high resistance is available. So no current flows through the operational amplifier because of infinite or very high input impedance. So if no current is flowing means what? Here the volt potential difference is 0. If the potential difference is 0 means what? So now here VA is equal to VB. Now if I am taking this as a VA and this is a VB, here the potential difference is 0 means what? VA minus VB is equal to 0. Thereby we can also say it as VA is equal to what? VB. But here VB is connected to the ground, so VA also acts like a ground. VA is not connected to the ground directly, but it is acting like a ground because of this very high input impedance. Potential difference across this impedance is 0. So whatever the voltage is available at VB, the same will be reflected on VA. Now VB is connected to the ground, so that's why VA is also acts like a ground. So this is called the virtual ground concept. What is virtual ground concept means what? Here this terminal is not connected directly to the ground, but it is behaving like a ground because of VB is connected to the ground. So now this is now for all the applications when we are going to derive the expression, now always I'll say that VA is equal to VB. Then why it is VA is equal to VB? Now here I have explained. Because of very high input impedance, no current is flowing into the amplifier, thereby the voltage drop across this resistor input impedance is 0. So that is nothing but what? VA minus VB is equal to 0 and VA is equal to VB. Always these two voltages are equal. Now after knowing this virtual ground, now I have to apply the KCL. Now apply nodal analysis, we are apply KCL at node A. Now this is the A node and the voltage potential at this node is VA and here this is the VB. Now here if all currents are leaving, why all currents are leaving? I have to apply the nodal analysis. What is nodal analysis? It is nothing but a KCL only, but one thing we are assuming that all currents are leaving. Why? Because this potential is higher than the remaining all potentials. Now if you write the KCL, then how to write? If I am taking this as I1 current, this is IF current and this is I in current or I in current. Then at the time what I can write? I1 plus IF plus I in is equal to 0. Where this current is also, this current is what? 0. Why it is 0? Already we have discussed that because of the very high input impedance. So here only we have to take two branches, that is this branch and this branch, I1 and IF. Then how can we write I1? I1 is equal to how to write? So VA, nodal analysis, VA minus VI divided by R1. So potential difference divided by this resistor is called the, gives the current flowing in this branch. Now the current is leaving in this direction means what? This potential is greater. So that's why we have to take VA minus VI divided by R1. Similarly, we have to write the expression for the IF. IF is nothing but what? Current flowing in this branch. Now here the potential is VA, here the potential is V0 and the resistor is RF. So VA minus V0 divided by RF is equal to 0. So this is a nodal analysis. Nodal analysis, what nodal analysis saying? All currents are leaving from that branch. Why all currents are leaving? We are assuming that wherever we need to apply the nodal analysis, that node voltage is higher voltage we are assuming. So that's why always you have to subtract the other potential from the reference. Now here VA minus V0. Now in this already what we have discussed, so virtual ground concept, what is that? VA is equal to VB. Why VA is equal to VB? Because no current is entering into the operational amplifier, voltage drop is 0, that's why VA is equal to VB. But VB is connected to where? It is connected to the ground. So this is nothing but a 0. So VB is directly connected to the ground. VA is not directly connected to the ground, but still it is acting like a ground. That is called the virtual ground concept. Now this is the expression number 1 and this is the equation number 2. Now substitute equation 2 in equation 1. So thereby what? VA, wherever VA is there, we need to put 0. So thereby what we get? Minus VI divided by R1 is equal to V0 divided by RF. Now I am sending this term to that side. So what we need to write? This, we are trying to derive the expression for gain. Gain is nothing but what? Output divided by the input. Now here V0 divided by V in is equal to minus RF divided by R1. This is nothing but a voltage gain of the inverting amplifier. Then what this minus indicates? Minus indicates the phase shift. Resistor value is not in the minus values. This minus indicates the inverted output. So we get the 180 degrees phase shift at the output. Now this is the gain formula. Now what is gain here? If you know the R1 value and RF value and how much gain you needed, depending upon that you can set the both the resistor values. So this is about the inverting amplifier. Now we derived the expression for the inverting amplifier. Now we will derive the expression for the non-inverting amplifier. So non-inverting amplifier means what? Signal we need to apply to the non-inverting terminal. That is to the plus terminal. To the plus terminal we are applying this signal. So here I am taking it as a VI, VS, however you want it to. Now this inverting terminal I have to make it to ground, and this is the output. Now feedback where we need to connect to the positive terminal or to the negative terminal? To the negative terminal. Why? Because always in the amplifiers we have to apply the negative feedback. Negative feedback means what? Part of the output should go to the negative terminal. Whether you are applying signal to the positive terminal or negative terminal, irrespective of that, you have to give the feedback to the negative terminal. And here I am taking the R1 and RF. The same notation I am giving in the inverting amplifier. Whatever the notation I have taken, I am taking this same notation. Now we need to derive the expression for this gain expression again. So now here I am taking it as a VB and this is the VA. Now currents are what? Two currents we will take. Now this current no need to take. Already why we no need to take? Already I have said that current is equal to 0. Now if you apply nodal analysis, apply nodal analysis at node A. Then here if I apply the nodal analysis, then what? Here the potential difference is 0. So VA minus 0 divided by R1 plus, now here for this, so VA minus V0 divided by RF is equal to 0. This is expression number 1. Now here VA, already we know that VA is equal to VB, but now in the inverting amplifier VB is connected to the ground, that's why VA is equal to VB is equal to 0 we have taken. Now in this case what? VA is equal to VB because of the high input impedance. But VB is not connected to the ground, VB is connected to the supply signal. So that is nothing but what? VI. So this is equation number 2. Now substitute this equation in the equation 2 in equation 1. Then we get, so substitute in equation 2 in equation 1. Then if you rewrite this, VI is equal to, we need to write VI. So VI divided by R1 is equal to VI, plus VI minus V0 divided by RF is equal to 0. Now all VI terms we write together. VI I am taking common. So 1 divided by R1 plus 1 divided by RF. V0 if I am sending to this side, V0 divided by RF. So we need to write expression V0 divided by VI. This is nothing but what? Gain. So now if I send this RF to this side, so RF into 1 divided by R1 plus 1 divided by RF. So if we rewrite this expression, then we get V0 divided by VI is equal to, so write this and take the LCM and rewrite the expression, then you will get 1, so RF by R1 plus 1. Now take R1 common, so then so we will get R1 plus RF divided by R1. Otherwise here you can stop here, 1 plus RF by R1. This also you can write it as AV is equal to 1 plus RF by R1. Now this is the expression for the gain expression for in the case of non-inverting amplifier. So by choosing the R1 and RF, you can decide the gain, and here you are going to get the waveform like this. If this is your applied waveform V in, now here you are going to get magnitude will increase, but with the in phase. So this is the output. So now this is about the inverting and non-inverting amplifier. In the next lecture we see the adder and subtractor.